Welcome back, everyone, to MAE170. This is lecture 11 in week number 7. So now we're ready to use what we learned in the past weeks in order to design a kind of controller that is known as phase lead or phase lag compensator. Here we have a name, compensator, and not really controller, but you have to think about these compensators as controllers. They really play the role of a controller. And in fact, the name compensator comes from the fact that a non-compensated system, so let's say that we have a plant with its transfer function, usually g of s, and let's say that we have the opportunity of regulating the gain, so the constant k. We close the loop and we see that our system does not meet the requirements that we would like it to meet. For instance, it doesn't reach the percent overshoot requirement or the settling time requirement. And so the first thing that you want to do before considering adding a controller / compensator is to try and modify the plant as much as possible. That is, what you want to control or you would like to control. So if there's a way for you to modify the plant so that you meet your requirement, then there's no need to implement and design a compensator. However, if you've done everything in your power to modify the plant, and there's no way you can reach the requirements even by changing the constant gain k, then at that point, you have to compensate the deficiencies of your plant by adding a compensator, hence the word compensator. But for what we've seen so far, the compensator really, as I said, plays the same role as a controller. All right, so starting from the uncompensated system, the closed loop transfer function is our usual kg over 1 plus kg. So this is going to be our uncompensated closed loop transfer function. Now, once we add the compensator, well, here the compensator, we're just going to consider it in series with the gain and the plant. So it's really in the usual place that we would normally find the controller. As a matter of fact, let's just use GC as it was a controller. So, but, again, gonna use the word compensator. And we still have our gain and our plant. So how does the closed loop transfer function change now? Well, this is going to be equal to k gc g over 1 plus k gc g. All right. So now what is the nature of the compensator? Let's say that we don't really care now what g of s, sorry, not GC, g of s looks like. We want to focus on the structure on the compensator. So phase lead or phase lag compensator have both the same structure, and this is the following. In the S domain, they have a transfer function that is a fraction, and at the numerator, we have a first degree polynomial, s plus sigma z, and at the denominator, we have s plus sigma p. If you think about it, it's like we were adding one real zero, of course, and one real pole. So in terms of poles and zeros, the introduction of a phase lead / lag compensator is equivalent to adding one real zero and one real pole. So typically the values for sigma z and sigma p are positive. That is, the 0 and the pole are both negative. In fact, the location of the 0 is going to be minus sigma z, and therefore that is negative. And the p is equal to minus sigma p, which is also negative. So the pole and the 0 that we are introducing using a lead or a lag compensator are negative and real. All right. So sometimes you'll hear me say just lead or lag compensator. I will drop the word phase. But technically speaking, we're talking about phase lead or phase lag compensator. So why are they called phase lead or phase lag compensator? Well, it will be clear next week, but I will describe this feature right now. So when we use a lead compensator or phase lead compensator, the response to the compensated system will be shifted in terms of phase forward. We're going to add some phase to the uncompensated system. On the other hand, if we were to use a phase lag compensator, we would be subtracting some phase to the uncompensated system. So let's see visually in the S-plane what this means. Let's start from the phase lead compensator. And again, most of the times I'm just going to call them lead compensator. All right, so for a phase lead compensator, we require minus sigma p to be less than minus sigma z, and both are less than 0. In other words, the pole, which is a negative real number, is to the left of the 0. So let's draw that on the S-plane. Since both the pole and the 0 of the compensator are real and negative, then they must lie on the negative portion of the real axis. For a phase lead compensator, the pole is to the left of the 0. So for instance, we can have the pole here and the 0 right here. So here we are at minus sigma p, and the 0 is at minus sigma z. Therefore, minus sigma p is less than minus sigma z. So in order to understand why for a lead compensator, or why a lead compensator adds some phase, let's consider a generic point on the complex plane, S equals to sigma plus I omega. So if we are adding a lead compensator, now what we're going to do is we're going to see the angles that this generic point is making with the pole and the 0. So when it comes to the 0, we have that the angle associated with it is, we're going to call it theta z. And the angle associated with the pole, we're going to call it theta p. So the angle for the lead compensator, it's going to be the angle of the 0, which is always, we add the phase of the 0 because it is at the numerator of our transfer function, and we're subtracting the phase of the pole. You can see from the picture here that theta z is greater than theta p. Therefore, theta z minus theta p is a positive value. So we're adding some phase. Let's just prove it really quickly. So as I just wrote, the transfer function of our lead compensator is S plus sigma z over S plus sigma p. So what is sigma z? Sorry, S here is our generic point on the complex plane, which is sigma plus I omega. So we're gonna substitute that in here. S equals sigma plus I omega. So our transfer function will now look like the following: sigma plus I omega plus sigma z over sigma plus I omega plus sigma p. So what is the phase, the overall phase associated with the lead compensator? We have to take the angle or the phase of this complex number. So remember, when we're calculating the phase of a complex number that is written as a fraction, we have that this is going to be arctangent of, and first refer to the numerator, so plus arctangent of imaginary part. What is the imaginary part of the complex number at the numerator? Well, it's simply omega over the real part of this complex number. What is the real part? It is sigma plus sigma z. Now to conclude, now we have to subtract the phase associated with the complex number at the denominator of the fraction. So we do the same. Now it's minus arctangent of imaginary part. Once again, the imaginary part is omega over the real part. In this case, we have sigma plus sigma p. You can see from the S-plane that sigma plus sigma z is really the distance on the x-axis between the 0 and the generic point S, and sigma plus sigma p is the distance on the x-axis between the generic point and the pole. So we have sigma plus sigma p. For both the 0 and the pole, the y distance is equal to omega. So that's how you define theta z and theta p. In fact, we have that theta z is arctangent of omega over sigma plus sigma z, and theta p, I missed the Greek letters, is arctangent of omega divided by sigma plus sigma p. You always have to think about the arctangent, the numerator of the arctangent function as the sine and the denominator as the cosine. So if we take, for instance, this triangle, then the sine would be associated with omega and the cosine with sigma plus sigma z. All right, so since sigma z sorry, I have to move this down here. All right. All right, so since theta z minus theta p is positive, then overall we're adding some phase. So the lead compensator adds some phase to the uncompensated output. Now we can do the same reasoning for a lag compensator. Now, what is the difference between a lead and a lag compensator in terms of positioning the pole and the 0? Well, it's going to be the other way around. That is, now that the real 0 is to the left of the real pole. So we're going to have the 0 to the left of the pole. And so now you see that theta p, so the phase associated with the pole, is greater than the phase associated with the zero. Therefore, the overall phase angle associated with the overall lag compensator, being theta z minus theta p, is negative. So we are subtracting some phase to the uncompensated system. So that's the reason why they are called lead and lag compensators, but phase lead and lag compensators. This is going to be used, the fact that we can add or subtract some phase is going to be used later on. We're going to see it most likely at the end of week 8 or at the beginning of week 9. But for now, we're going to use compensators just to, or we're going to design such compensators using the root locus. And in the root locus context, these two compensators are used for completely different purposes. So we don't really care about the phase. But in fact, what we care of is the following. So we're going to use the lead compensator to, you can think about it as adjusting the root locus. And by adjusting the root locus, I mean that if we want our root locus, let's say that our root locus looks like this. And we're going to see an example of it. And somehow we want it to pass through some locations. And there's nothing that we can do, because even if we change the value of k, we can only go, sorry, let's say it's like this. This is correct. We can only stay on the root locus. We will never be able to pass through these green squares or the locations of the dominant poles that we wanted. So we need to bend the root locus. So the lead compensators is exactly used to do this. We can bend the root locus in order for it to pass through the desired location of the dominant poles of our closed loop transfer function. So let me repeat once again. Lead compensator is used to modify the uncompensated root locus so that it will pass through a certain location that we want. The lag compensator, instead, although it kind of does the same thing because both compensators will modify the root locus, but the main purpose for the lag compensator is just to decrease the steady state error without changing the system type number. This can be used if and only if we already have a steady state error that is finite, because only if we have a finite steady state error, we can reduce it to a smaller value. If the steady state error is already infinite, then even by introducing a lag compensator, there's nothing that we can do. The only way to decrease the steady state error would be to increase the type number of the system. But if we don't want to do that, and we have a finite steady state error that unfortunately does not meet our requirements, then we can introduce a lag compensator in order to meet such requirements. But these are strictly in terms of steady state error. And of course, if your steady state error is already 0, then you really don't need a lag compensator. What if you wanted to both adjust the root locus and meet the requirements for the steady state error? Well, you can use both a lead compensator plus a lag compensator in series. And so we're going to refer to this combination of compensators as a lead lag compensator. And the transfer function associated with the lead lag compensator is just the product of the transfer function for a lead compensator. So we have S plus sigma Z lead over S plus sigma P lead times a transfer function for a lag compensator. So in total, if you are introducing a lead lag compensator from the complex plane perspective, we are adding two real poles and two real zeros to the uncompensated system. So typically, this is how the zeros and the poles for a lead lag compensators are placed. So for a lead compensator, again, we have the pole to the left of the zero, and they can be quite spaced out, such as this. Instead, when we have a lag compensator, both zero and pole will be very close to one another, and both are close to the imaginary axis. So in order for it to be a lag compensator, then we must have the pole to the right of the zero, but both of them will be quite close to the imaginary axis. So if the zero and the pole are very close to one another, such as in the case of a lag compensator, you see that the angle associated with the zero is almost equal to the angle associated with the pole. So this will cause the root locus of the uncompensated system not to change dramatically. On the other end, we have that the lead compensator introduces two angles that are quite different when it comes to the pole and the zero. Therefore, the lead compensator will substantially change the root locus of the uncompensated system. And that's exactly why we use the lead compensator part. So when we're designing a lead or lag or both lead and lag compensator in the root locus context, then the phase associated with the lead compensator, so the angle, and I'm just going to take it as an absolute value, is going to be greater than the angle associated with the lag part of the compensator. And in fact, the phase associated with the lag compensator is usually very small, most of the times less than 1 or 2 degrees. So here I'm using the absolute value because technically the phase associated with the lag compensator is negative. Okay. So here is just a warning that I've already talked about. That is, before trying and add a compensator, so before doing any sort of design, you must try to change the system as much as possible, because the compensators are kind of your last resort. If there's nothing you can do about your system, about your plant, then you can add a compensator. The last thing that I want to do before actually seeing some example is to take a look at the effect of both a lead compensator or a lag compensator to the steady state error. So as I said, the steady state error will change only if it's a finite non-zero number. So if we have for the uncompensated system that ESS is a finite number, then we're really considering just a few cases. For instance, we have a type 0 system associated with the step input. If you go back to one of the first lectures, you remember that the combination type 0 plus step input will generate a finite steady state error. Same thing can be said for a type 1 system associated with the ramp input and a type 2 system associated with an acceleration input. If we had, for instance, a type 2 system subjected to a ramp input, the steady state error will just be 0. So even if we added a lead or a lag compensator, the steady state error wouldn't change. All right, to demonstrate the fact that the lead compensator increases the steady state error and the lag compensator decreases the steady state error, let's consider one of these combinations. And in particular, let's consider a type 0 system coupled with a step input. So we have first the uncompensated system whose input is the step, that is 1 over S. So we have the gain, we have the planned G of S. And G of S being a 0 type, we can write it as N of S over D of S. You see that we don't have any pole at the origin. So what is the error? The error is the input minus the output. That is 1 over S minus ES times K times G of S, or E of S is equal to, maybe you're more familiar or remember this expression is R of S times 1 over 1 plus KG. And in this case, R of S being 1 over S, we have the following. Now that we have the error function in the S domain, we can find the steady state value applying the final value theorem. Now here we're going to assume that the final value theorem is applicable. But remember, before doing that, you always want to check the poles of the function to which the final value theorem you want to calculate. So in this case, we have the limit for S that goes to 0 of S times E of S. So we have limit for S that goes to 0 of S times 1 over S times 1 over 1 plus KG. So here S and S cancel out, and we're left with 1 over 1 plus KG evaluated at 0. Okay, so this is the steady state error for the uncompensated system. So this is what we have. If we were to add a compensator to the system, let's see how the steady state error changes. So now we have GC as usual as S plus sigma Z over S plus sigma P. Well, by the way, everything that I'm talking about is part of chapter 10. I will include the exact paragraphs on Canvas, but they're already included on the syllabus. All right, so now in this case, the error function in the S domain is 1 over S times 1 over 1 plus K. And now we have GC times G. So the only difference is the introduction of this GC, that is the compensator. All right, so once again, assuming that we can apply the final value theorem, the steady state value for the error, now for the compensated system, is equal to the limit for s that goes to 0 of s times e over s. So let's write it down, 1 over s times 1 over 1 plus k g times g. And so this is equal to 1 over 1 plus k gc evaluated at 0 and g evaluated at 0. But what is gc evaluated at 0? Well, consider gc, substitute s equals 0, then you're left with sigma z over sigma p. And for convenience, let's call this ratio 1 over alpha. So alpha is actually sigma p over sigma z. So for alpha greater than 1, we have a lead compensator because the value of sigma p is greater than the value of sigma z. And when we have the opposite, that is when alpha is less than 1, then we're talking about a lag compensator. So now let's take the ratio between the steady state error of the compensated system over the steady state error of the uncompensated system. And let's see if this ratio is greater than 1, it means that we've increased the steady state error. If this ratio is less than 1, it means that by introducing a compensator, we've decreased the steady state error. So we have 1 over 1 plus k times g evaluated at 0 over alpha over 1 over 1 plus k g evaluated at 0. So rearranging this fraction, we have 1 plus kg at 0 over 1 plus kg at 0 over alpha. So it is pretty evident that this fraction is greater than 1 if alpha is greater than 1. And this fraction is less than 1 if alpha is less than 1. In other words, we are decreasing the steady state error if we're choosing a lag compensator. So let me summarize it here. The steady state error associated with the lead compensator is greater than the steady state error associated with the uncompensated system. And the steady state error associated with the lag compensator is less than the steady state error associated with the uncompensated system. And this is exactly why we choose the lag compensator in order to decrease or in order to meet the requirements in terms of steady state error. So let's say that we have an uncompensated system that doesn't meet the requirements of settling time, for instance, but meets the requirements in terms of steady state error. So, well, we take care of the settling time by applying or by designing a lead compensator. But using a lead compensator will increase the steady state error. So let's say that now the steady state error does not meet our requirements anymore. So now we are with the settling time that is fine, but not with the steady state error. What do? Well, we simply add a lag compensator to take care of the steady state error. So it's always the order of the lead and lag compensator is always first the design for the lead compensator and only then the lag compensator. Because if you were to do the opposite, then you would mess up everything. So let's start with the lead compensator design. Of course, here we're using the root locus context. Then later on, we're going to see the design of still a lead compensator, but now in a different context, and that's going to be in what, well, you're probably already familiar with the Bodhi plot, but that's for later. So I'm going to show you a design for a lead compensator using an example, and then at the end of the example, we will summarize the points, the design points. So the goal that we have is to modify the root locus so that the modified root locus will intercept the desired location of the dominant poles of the closed loop transfer function. Let's start with the uncompensated planned transfer function. So let's say that we have g of s that is equal to 1 over s squared. And we have the following system specifications or requirements. We want the settling time to be less than or equal to 4 seconds. And we also have a requirement in terms of percent overshoot, and we want this to be less or equal to 35%. You see here, we don't have any requirement in terms of steady state error, so we don't really care about a lag compensator. But before doing that, we want to take care of settling time and the percent overshoot requirements. And therefore, we might want to design a leak compensator. But as I said, before even doing that, we have to see if the uncompensated system meets the requirement. Because if the uncompensated system already meets the requirement, we don't need the compensator at all. So how do we check that? Well, as usual, we can relate the system specification requirements to a pair of dominant poles of the closed loop transfer function. And this is regardless of the order of the system, because normally the dominant poles of a closed loop transfer function are a couple of complex conjugate poles. Even if the order of the system was more than 2, you take the 2 poles closer to the imaginary axis, and those are your dominant poles. So even if this, in this case, the system is a second order system, this is the open loop system, and also the closed loop system will be a second order system. But this step can be done for any order of the system. Even if we had a third order, fourth order system, you can always relate the requirements to the real part and the imaginary part of the dominant poles. So the dominant poles are in general equal to minus zeta omega n plus or minus I omega n times square root of 1 minus sigma squared. So why did I choose a complex conjugate pair of dominant poles? Well, because that's the most common and sought for choice. Here we want a percent overshoot that is less or equal to 35%. So as soon as we have even a little bit of percent overshoot, we are allowed to have complex conjugate poles. And I would always aim for those. All right, so let's now translate the requirements in terms of the damping ratio and the natural frequency associated with this pair of dominant poles. Starting with the settling time, we know that given a 2% criterion, the settling time is given by 4 over zeta omega n, and this has to be less than 4 seconds. So this implies that zeta omega n has to be greater or equal to 1, or minus zeta omega n has to be less or equal to minus 1. Now, what about the percent overshoot? Well, we have that the percent overshoot is always linked to the damping ratio. And that is equal to 100 times e to the power of minus zeta times pi over square root of 1 minus zeta squared. So this has to be less or equal to 35. Now here I've skipped a couple of steps, but so it's up to you to do that because you will be asked to do so later, but we don't really have the time to do so. But you can find quite easily that zeta has to be greater or equal to 0.32. Or if we're looking at the angle that the line connecting the origin with the couple of dominant poles makes with the negative part of the real axis is less than 71 less or equal to 71.3 degrees. Remember that theta is arc cosine of zeta. Now, as we already know how to do, we can draw the requirements in terms of settling time and percent overshoot on the S-plane. So if we start with the requirement connected to the settling time, we wanted the zeta times, where is it? Here. Zeta times omega n to be greater or equal to 1, or better, this one is better because minus zeta times omega n is exactly the real part of our dominant poles. So we want the real part to be less or equal to -1. So we are going to exclude everything to the right of -1. We're going to exclude a priori the left-hand side of the complex plane because that represents the unstable region, and obviously we don't want an unstable system. So the excluded region will have these marks here. So we can actually choose any point to the left or even on this line. But we have the other requirement, and that is the one connected with the percent overshoot. So now we have the line starting from the origin. Obviously it has to go both ways, up and down, and the angle that this line makes with the negative real axis is what we found to be 71.3 degrees. And we want everything below. So we don't want this region over here. This is excluded. So if we combine the requirements, we can choose any couple of dominant poles here. So in this case, this is up to you. This is an arbitrary part of the design. And as I said already many times, this is something that it's actually good for engineers. You want to have infinite choices. It's better to have infinite choices than just have one choice, because if that one choice then later on proves not to work, well, then you're in trouble. So here we have an infinite amount of choices. So let's choose this pair of dominant poles. And so this is, I chose them as -1 plus I2 and -1 minus I2. They lie on the region. And so we can proceed using our dominant poles as -1 plus or minus 2i. All right, very well. Now that we know where our dominant poles are, we still have to check whether or not our uncompensated system's root locus will pass through the location of these dominant poles. So what do we need to do? Well, we need to draw the root locus for the uncompensated system. So let's go back to our uncompensated system. We simply have our gain k, and our plant is 1 over s squared. So what is the closed loop transfer function for the uncompensated system? That is k times 1 over s squared over 1 plus k times 1 over s squared. Well, you see that the characteristic polynomial is already in the canonical form for the root locus. And this is very easy because our g of s being 1 over s squared has only two poles, two open loop poles at the origin, both of them at the origin. None of the real axis belongs to the root locus, and the root locus for this case, in this example, is simply the imaginary axis. We have two asymptotes, and when we have two asymptotes, they always depart. They make 90 degrees with the real axis. And this is it. This is the uncompensated system root locus. You can see that no matter how much we change the value of k, this root locus does not pass through the dominant poles that we chose, which are over here. Even if we had chosen another pair of dominant poles, the uncompensated root locus would be in the forbidden region. Right? The imaginary axis is on our forbidden region when it comes to meeting the requirements, the specifications. So indeed, we need to introduce a lead compensator to bend the uncompensated root locus so that it'll pass through the dominant poles. So this is S, we're going to call it dp1 and S dp2. All right, so we need a lead compensator. Of course, we're talking about lead compensators. So I was going to choose an example for which the lead compensator was needed. All right, so we have S plus sigma Z over S plus sigma P. And the other thing that we want alpha, that is sigma P over sigma Z, to be greater than 1. So this is the second one is the condition for a lead compensator, because the transfer function is the same for lead or lag compensator. But we definitely want a lead compensator because we want to modify the shape of the root locus. So now if we go back to our block diagram, always with 1 over s squared for our plant, our gain k, but now we also have our compensator. So what is the objective? Well, we want to find values for sigma z, sigma p, and eventually also of the gain k. I fused the two words and turned out cane, but it's actually the gain k, so that the dominant poles of the closed loop transfer function are exactly what we chose. All right, so the first step is to actually compute the closed loop transfer function. So our GC is S plus sigma Z over S plus sigma P times 1 over S squared. And at the denominator, we have 1 plus K S plus sigma Z over S plus sigma P times 1 over S squared. All right. So as I said, we have three parameters that we have to determine. K, the location of the zero, and the location of the pole. So in other words, the dominant poles of the compensated transfer function have to satisfy the characteristic equation. So we have to satisfy 1 plus k times s plus over s, blah, blah, times 1 over s squared equals 0. And this has to be valid at the location for the dominant poles. So here I can either choose -1 plus 2i or -1 minus 2i. For this example, I'll just use -1 plus 2i, but it's the same. You can choose either the other one, because if the root locus passes through one complex number, it will have to pass through its complex conjugate. All right. First step is the easiest. It's just a determination of the zero. And this is kind of an arbitrary step. So in other words, there's not a fixed rule, there's a rule of thumb. And this rule of thumb tells us that we're going to place the zero, that is sigma z, exactly where our complex conjugate dominant poles are. So since the zero is real and the dominant poles are complex conjugate, how do we do that? Well, we choose the zero to be equal to the real part of the dominant poles. And so in this case, we have absolute value of -1, it is 1. So first step, very easy, arbitrary. Once we know the location of the dominant poles, we're gonna use the real part to determine the location of the zero of the compensator. So if we go back to the S-plane, we would do the following. We would just project the dominant poles onto the real axis, and we'll use this location on the real axis as our zero. So we are at minus sigma z. And this is an arbitrary step. However, now the determination of sigma p and k will be forced, because now we have to satisfy the characteristic equation. In other words, we have to satisfy 1 plus k times s plus, and now we know that our sigma z is 1, so it's s plus 1 over s plus sigma p, we don't know sigma p yet, times 1 over s squared equals 0. And this has to be valid at our dominant poles. So as I said, we just have to use 1, and we're going to use the -1 plus 2i. So in other words, we're going to substitute this into the characteristic equation here, here, and here. And so we have that k times -1 plus 2i plus 1 over -1 plus 2i plus sigma p times 1 over, now we have s squared, so -1 plus 2i, everything squared, has to be equal to -1. So you see that now we have two unknowns, sigma p and k. And apparently, we only have one equation. But if you go back to when we introduced the root locus, I told you that when we are satisfying the characteristic equation, since it's a complex equation, that can be broken down into two equations. And in particular, we have the phase equation and the magnitude equation. Now, if we start with the phase equation, we can directly determine sigma p. So what is the phase equation associated with the left-hand side of this characteristic equation? All right, so the phase associated with k is arctangent of 0 over k. That is 0, because k we assume it to be positive. So that's why k will not be determined using the phase equation, but only sigma p. Now we go ahead with what we have at the numerator. At the numerator, we have minus 1 plus 1, they cancel out, so we simply have 2i. So plus arctangent of imaginary part, which is 2, over real part, which is 0. So arctangent of infinity, since both signs are positive, this is 90 degrees. We don't have anything else at the numerator, so we have to look at the denominator. Now at the first complex number at the denominator that we're finding is minus 1 plus 2i plus sigma p. So we have minus arctangent, and the minus is because, once again, we are at the denominator. Imaginary part, which is 2, over real part, that is sigma p minus 1. And then we do the same with the other complex number, minus 1 plus 2i. So since we have that this is elevated at the power 2, we are subtracting 2 times arctangent of the imaginary part, which is 2, over the real part, that is minus 1. And this has to be equal to the phase associated with the right-hand side, minus 1. And for what we saw, the phase of minus 1 is 180 degrees. And again, plus n 360, where n is an integer. All right, so arctangent, let's start with the fact that arctangent of 2 over minus 1 is equal to 116.57 degrees. So we'll leave on the left-hand side only the term containing sigma p are unknown. So we have minus arctangent of 2 over sigma p minus 1. That is equal to 323.13 degrees plus n 360. Now we change the sign. So we have arctangent of 2 over sigma p minus 1 equals minus 323.13 minus n 360. Now here on the right-hand side, we want an angle that is between 0 and 360. So if we choose n equal to minus 1, then here we have minus 323.13 plus 360, that is 36.87 degrees. Now, if we take the tangent of both sides, then we are left with 2 over sigma p minus 1 equals to tangent of 36.87. Or sigma p is equal to 2 over tangent of 36.87 plus 1, which happens to be a very nice fraction, 11 over 3. So now we know the location of the pole. Let's check if it's indeed viable. For it to be a lead compensator, the pole has to be to the left of the 0. So 11.3, 11 over 3 is about 3.7. So we would be about here at minus 3.666 or minus 3.7. So indeed, the pole is to the left of the 0, and so we're actually dealing with the lead compensator. You always have to check that. So if you were to take the ratio between the pole and the 0, that is alpha, that is greater than 1. But we still have to determine exactly the value of K so that the dominant poles are exactly what we want. And now we're going to use the remaining equation, that is the magnitude equation associated with the characteristic equation. So let's go back here. And now we have that the magnitude of K is simply K. Then we have the magnitude of 2i, which is 2. And we don't have anything else at the numerator. At the denominator, we need the magnitude of sigma p minus 1 plus 2i. And so what is the magnitude? That is the square root of the real part squared, real part being sigma p minus 1 squared, plus the imaginary part squared, which is 2 squared. And then we have still at the denominator the square root of the real part of minus 1 plus 2i, which is minus 1, so squared, plus the imaginary part squared. And since we have this complex number twice, this is elevated by 2. And this has to be equal to the magnitude of minus 1, which is simply 1. Now we know that we've just found that sigma p is equal to 11 over 3. So we have that K times 2 over 64 over 9 plus 4 times 1 over 5 has to be equal to 1. Or if you rearrange this, I skipped a step here, but it's going to be in the notes. K is equal to 25 over 3. So the overall characteristic equation becomes 1 plus 25 over 3 times s plus 1 over s plus 11 over 3 times 1 over s squared equals 0. And the two poles of this characteristic equation are exactly minus 1 plus or minus 2i. Now, if we were to draw the root locus associated with the compensated system, so in order to do that, we would need to just let k vary. So really considering 1 plus k times s plus 1 over s plus 11 over 3 times 1 over s squared equals 0. Now let's see how this changes. We still have the two poles at the origin. So I'm going to use now the green color for the compensated system. We still have the same two poles, but now we have a 0 at minus 1, and we have a pole at minus 11 over 3. So let's see. What segments of the real axis belong to the root locus? We have two poles at the origin, so nothing. Then we encounter minus 1. So everything that is contained between minus 1 and minus 11 over 3 belongs to the root locus. And the segment going from -11/3 to -1 is just a branch of the root locus. So the other two branches have to stem from the two open loop poles at the origin. And they will leave perpendicularly to the real axis, but then they will bend and they will pass through the dominant poles. And you can also calculate the location, the exact location of the centroid asymptotes. So you'll see what the two branches of the compensator root locus will go towards. But the important thing is here we were able to modify the root locus of the uncompensated system in yellow already written here. Here we go. So that now it finally passes through the locations of the dominant poles that we wanted. And in particular, since we exactly want the location of the dominant poles, we know that the value of K that we calculated for when the root locus passes through the dominant poles is equal to 25/3. All right, so this was an example that showed you how to design a phase lead compensator using the root locus methodology. So in order to recap the steps, let's read them together. We start one, determining the location of the desired dominant poles using the system specifications. So if you have specifications or requirements in terms of settling time, percent overshoot, peak time, rise time, then you translate them into regions of the complex plane that you can choose on which you can pick your dominant poles. And eventually you have just to pick one location, which means that you have to determine a damping ratio and a natural frequency. And of course, this is valid assuming that the system will behave approximately like a second order system. In the example that we saw, we had exactly a second order system, but if we were dealing with a system that was order 3, 4, or so on and so forth, then it's all an approximation for its dominant poles. So the dominant poles are usually written in the form as a complex conjugate numbers. And so you can use the values of zeta and omega n to find exactly the location of the dominant poles on the complex plane. Then what you want to do is to sketch the uncompensated root locus and see whether you can get to the desired dominant poles by simply changing the gain k. So check the root locus of the uncompensated system, because if it passes through the dominant poles that you want, then you're fine. You don't need to design a lead compensator. However, if changing k is not enough, then what you want to do is you want to consider a lead compensator. So we need to determine the location of the zero and of the pole. Starting with the zero, and you place the zero of the lead compensator directly below the desired dominant pole location. So you take sigma z equal to the absolute value of zeta times omega n, or something that I didn't mention earlier, to the left of the first two real open loop poles, if they are in the way. So let's say that you had your dominant poles location right here, but it happens that your uncompensated root locus or system has one pole here and one pole, the second pole is here. So instead of selecting the 0 of the compensator right below the dominant poles, you just select the location slightly to the left of the second open loop real pole, if that is the case. But again, step 3 is arbitrary. That's why you don't really have to determine or pick the location of the 0 right below the dominant poles. That's why you can also choose it a little bit towards the left. Now, though, once you've picked the 0, you must pick the pole so that it solves the phase equation associated with the characteristic equation. And that is, you determine sigma p by solving the phase equation evaluated at your dominant poles. And then you have the chance of determining k by solving the magnitude equation at the dominant pole location. Now, step 6, I haven't really talked about, but you can always do that. If you have requirements in terms of the steady state error, then calculate the steady state error of the compensated system. And if not met these requirements, you can add a lag compensator. However, the important thing is that at the end of your design, you have to put your system together, your compensated system, and you have to go back to step 1 and verify that the original requirements are met. And if not, you have the chance of changing 2 things. You can change the location of the dominant poles. If you have a region of the complex plane to choose from, you can always change the location of your dominant poles, or you can change the location of your real 0 for the compensator. Remember, those were 2 arbitrary steps, or you can choose different values for both. And always check that the ratio between the pole and the 0, that is alpha, is greater than 1. All right, with that being said, I've concluded what I wanted to show you about the design of the phase lead compensators using the root locus methodology. Next time, we're going to take a look at the design for phase lag compensators, and then we're going to talk about proportional integral derivative controllers, also known as PID. Okay, this is all for today, and I'll see you virtually next time. Take care.